Hello guys, welcome to econometrics. When I'm looking at the vector autoregression, so a few days back we asked question of the month, which is regression analysis possible for time series data stationary at first difference but are not cointegrated? The question is yes. Regression analysis is possible for time series data stationary at first difference but not cointegrated. Now, what is that regression analysis? It is a vector autoregression, otherwise popularly called VAR. And vector autoregression is a regression analysis to estimate the relationship among variables that are stationary but not cointegrated. Okay, and let's look at a wider scope of VAR. VAR is a model used to capture the linear interdependencies among multiple time series variables. So VAR is a tool used to study how multiple time series variables interact with each other over time. And instead of assuming one variable affects another variable in just one direction, VAR lets all variables influence each other through their past values. Now, why do we have to use VAR? Because VAR focuses on short-run dynamics without requiring a long-run relationship. So VAR models multiple dependent variables simultaneously. So VAR provides a robust framework for forecasting and causality testing. VAR traces how a shock to one variable affects others over time. And lastly, VAR measures how much each variable contributes to fluctuations in others. Now, what are the steps to carrying out a vector autoregression? The first one is to check stationarity using ADF or Philipperon test. The next one is to ascertain if long-run relationship exists between variables using the Johansen test. The third one is to specify VAR equation. The fourth one is to select optimal lag length. The fifth one is to specify VAR equation with appropriate lag. And the sixth one is to check model diagnostics. The seventh is to interpret individual lag effects using T statistics. And the eighth one is to interpret dynamic effects using the impulse response function. And the ninth step is analyze the variance decomposition. Now, what we have to do now is go through the first step. Check stationarity and ascertain cointegration. To do that, we have to specify a model, a functional form of it. We say real GDP is a function of education and health spending. Now, to specify the model, we should keep in mind that all variables are what endogenous. For example, real GDP is a function of past value of real GDP and past values of education and health expenditures. And also, education is a function of the past value of real GDP and the past values of both health and education expenditures. And the third one is health expenditure is a function of the past value of real GDP and the past values of education and health expenditures. Now, we're going to look at check the stationarity of the three variables, and then we have to ascertain if long-run relationship exists among them. So we'll now go to our Eviews platform. Okay, this is the education, this is health, this is real GDP. So let us check the stationarity for real GDP. We go to unit root test, standard unit root. Let's check the ADF test at level. Okay, at level for ADF, real GDP is not stationary. Okay, let us see at levels for Philipperon. Okay, it is not, real GDP is also not stationary at level for Philipperon. Let's check first difference for ADF. Okay, real GDP is stationary at first difference for ADF. Let us check that for Philipperon to be sure. Okay, real GDP is also stationary at first difference for Philipperon. Okay, let us see that of education expenditures. Okay, for at levels for ADF. Okay, education spending is not stationary level. Let us see for Philipperon. Education expenditure is also not stationary at level for Philipperon. using Filiperon. Let us use the ADF first difference. Education spending is not stationary at first difference using the ADF framework. Let us also use go to Filiperon first difference. Good. Education expenditure is stationary at first difference using the Filiperon unitary test. Let's see that of health. Okay, view. Okay, let's check the levels for ADF. Using the ADF framework, health spending is not stationary at level. Let us check that of Filiperon. Also for Filiperon, health expenditure is not stationary at level. Let us check ADF at first difference. Okay, it's not stationary at first difference using the ADF framework. Let us check that of Filiperon first difference. Good. So health expenditure is stationary at what? At first difference. Okay, now we have real GDP first difference using the Filiperon. Good. We also have educational spending stationary at first difference Filiperon. Good. And health spending stationary at first difference using Filiperon. And the next step for us is to check for cointegration. This is the group data. Check for cointegration. Click on view. Go to cointegration test. Then the Johansson. Then we click OK. Okay, this is the cointegration test. Okay, the cointegration test shows no cointegration. Now let us look at an expanded view of it. Now this is the cointegration test. The rank test shows that the trace test indicates no cointegration at the 5% level. Also for the Maxenge value test indicates no cointegration at 0.05 level. So we conclude that real GDP, education and health expenditures are stationary at the same level of stationarity, at first difference. And also there is no cointegration or long run relationship among the variables, among real GDP, education spending and health spending. Okay. So for our first and second steps, we've discovered that the variables are stationary at first difference and that there is no cointegration. Now what is the next step for us to do? The next step is to specify our VAR equation. And then to select optimum lag length. Okay, let us go and specify VAR equation. We click on quick, estimate VAR. This is a VAR equation. And what you do when you specify the equation using the variables, you will use their first, you have to include the first difference of the variables. I've decided to log the variables dlog real GDP, then dlog education spending, then dlog health. We need to specify, make sure that the data we specify is in their first difference. Okay, we click on OK. Then once we've done that, the next step is for us to select optimal lag length. Okay, select optimal lag length. We'll click on view. And then once you click on view, we'll go to lag structure. Then we'll click on lag length criteria. Let us put 5 lags to include 5. Okay, that is our lag length. At econometrics information criteria, we have 2 lags. Let us put 6. Let's put 6 lags to see if we will still get the same thing. For 6 lags, okay, 6 lags we still have 2 lags. We still have 2 lags in selection criteria. Let's have an expanded view of it. Okay, this is it. Now please note that you have to specify the variables in their first difference, and then in order to decide the selection criteria, all we have to do this is what we decided, lag 2, using the econometrics information criteria. The next step, that is step 5, is to specify VAR equation with appropriate lag. And when I say appropriate lag, meaning this lag must be devoid of autocorrelation. Remember, initially we had 2 lags, and now we need to make sure that at these 2 lags there is no autocorrelation. Then step 6, we have to check model diagnostics, and step 7. And let us go to this to make sure that these 2 lags is devoid autocorrelation. Click on view, go to residual test, click on autocorrelation test, and then let us include 6 like we did. Now when we look at this autocorrelation test we did for the lag, we discovered that at lag 2 there is serial correlation. The null hypothesis is that no serial correlation, but at lag 2 it is significant, meaning there is serial correlation. When we come down here to at lag 2, it is significant at 5%, meaning that there is serial correlation at lag 2. So to ensure that there is no serial correlation in the model, we take the next one, which is lag 3, which shows that there is no serial correlation using lag 3. When you check here too, also we take lag 3, meaning that there is no serial correlation at lag 3. Okay, so that is for step 5. Then when we look at the expanded version here, we will now discover that this is the new lag for our study. Instead of 2, we now have 3, lag 3. So why specify? Initially we specified 1, 2. Now we're going to change and specify 1, 3. So instead of 1, 2, we use 1, 3. Okay, let's go back to our VAR and estimate. So instead of 1, 2, we use 1, 3. Yes, we use 1, 3. Click OK. Yes, so this is now our VAR results. The VAR result. See, just like we did here. So now we have ascertained specified VAR equation using the appropriate lag 3. We now go to check our model diagnostics. Check the model diagnostics to ensure that the model is okay, and then we'll now interpret individual lag effects using T statistics. Okay, let's check the model diagnostics. The first thing we have to do is to check for stability of the model. Check if the model is stable. Yes, you see all the dots are within the cycle. Within the cycle, this shows that our VAR model is stable. The dynamic model is stable. Okay. The next thing for us to do is to go to our residual test. We have checked for autocorrelation, and we'll check for normality test using the collect key of covariance. Okay, we now discover that the joint Jagbera test for normality shows that residuals are multivariate normal. See, so concerning normality test, the dynamic model is okay. Then we'll now go to our white heteroscedasticity. We use no cross terms. Look at the joint test. Probability of 0.5143 shows that the VAR residual heteroscedasticity test shows that the VAR or the dynamic model has an equal spread. Okay. Now that we've ascertained this, let us look at the expanded version of this. We discovered that using the diagnosis test that the VAR model is stable using the AR root graph. Also discovered that the residuals in the VAR model follows normal distribution using the joint Jagbera test. We also discovered that residuals in the VAR model are not heteroscedastic, that is homoscedastic. Okay. Now the seventh step is to interpret individual lag effect using T statistics. Now this T statistics here, this is T statistics in this bracket. We have to look at them. Now let us look at an expanded version of it using the PowerPoint. Now this is the result we just did now. This is the result. The third numbers in brackets are the T statistics. And so when the absolute T is greater than 1.96, then we can say that relationship is significant. Now we'll look at this result here. We can see that 2-year lagged education spending, negatively affects real GDP. Also, 2-year lagged health spending. Unlike that of education, positively affect real GDP. And then we'll come here and now say a 3-year lagged real GDP, the growth of the economy 3 years ago, affects what? Education spending positively. They will now also look at that 1-year lag health spending positively affected education spending. Also look at this other one, 2-year lagged real GDP negatively affected what? Health spending. The effect is negative, displayed by this minus 4.117658. And also a 1-year lagged health spending affected its own health spending negatively. So we'll now see that yes, 1-year lag health spending negatively affected health spending. Now the good thing about the VAR is step 8 and step 9. And step 8 is to determine the dynamic effect using impulse response function. In short, the VAR was designed to examine step 8 and step 9. So we have to look at them carefully. Now we'll now go to how do we do this? How do we determine dynamic effects using impulse response function? We'll now go to our Eviews, click View, we'll go to impulse response. We leave it this way. And then we press OK. Just see an expanded version of it. Good. This is it. This is impulse response. The response of GDP, or real GDP to real GDP, innovation, response of real GDP to education, the rest. Now let us look at the interpretations of the dynamic effect. Now for the first one, you can see that the impulse response function traces the effect of one-time shock to one of the innovations on current and future values of the endogenous variables. Now we look at the first diagram, first one, response of real GDP to real GDP. Now we look at a very initial positive boost to GDP, but falls and then stabilizes. See, and then we'll look at the second one. We discover that there is no education spending has no immediate effect on real GDP, but real GDP declines slightly after initial shock. But you can now see that it goes positive from here. It shows that this positive is medium term, it's not long term. So medium term positive effects after the dip, then now discover that long term stabilization at 0. The same one we have here, response of real GDP to health. Discover that real GDP did not react, the growth did not react instantly on health spending, but going to 1%, then a 1% shock to health spending, positive shock to health spending, and then the positive effect fades. It's coming down over time. It shows what? There is no permanent impact on GDP, no permanent impact at all on GDP, since it stabilizes. It goes up, then come down. There's no permanent impact. And when you come here, you see a response of education to real GDP, innovation. You see the positive real GDP shock leads to immediate drop in education expenditure. Positive GDP shock drops. Immediate drop in education expenditures, and it deepens to this level. And later on, maybe there is funding for education, and since there's funding for education, it comes up. GDP growth stabilizes. However, there is no lasting impact. There's no lasting impact that stabilizes. The next one is that GDP would boost initially. Response of education to response of education. Okay, we look at this way: response of health to real GDP innovation, and we discover the boost first, the positive boost first by 0.1%, but the health spending plunges below the baseline to 0.0 line. Maybe it suggests delayed austerities. However, there's temporary rebounds. Temporary rebounds occur, but the effect is quicker than the initial. So spending falls again and the response converges to zero. It shows that there is no permanent change to health expenditures. So that is how it is interpreted. You can also interpret the rest like that too. And once we've done that, the next thing we do is the variance decomposition. How do we do the variance decomposition? Now come to our Eviews. Okay, we go to view, click on variance decomposition. We leave it this way and we'll click OK. Now this is the variance decomposition. So you can see a lot of GDP coming down to itself from 100 down. I prefer using the stacked graph. We'll go to an expanded version of it. Let's look at the variance decomposition. Now, the variance decomposition analyzes the relative importance of different shocks in explaining the variation in each variable of the VAR system over time. It shows the percentage contribution of each variable shock to the forecast error variance of other variables. Now, when we look at the variance decomposition of real GDP, denoted by this blue, denoted by this blue, you see the first period, GDP is mostly self-driven, down to period 10. You see, real GDP takes majority of the spaces. So real GDP's variation is mostly self-driven. Nothing drives it except itself. Now, but when we look at the variance decomposition of education, it shows that from period 1 to 10, education's variation dominates early, but this influence declines as real GDP shocks gradually explains some shares. Real GDP, see, explains some shares, also responsible for variations in education spending. So we'll look at the variance decomposition of health here, depicted by the green color. We'll discover that from period 1 to 10, real GDP shock has considerable share too to it. See, health spending has also its own variation, but GDP contributes more than even what education expenses. So that is how we interpret the variance decomposition in the VAR setting. So we thank you very much for your attention.